Welcome to the MSJC Internet Authoring Videocast.
In this video, you'll be learning about the Internet and the World Wide Web. The objectives for session A1 are you'll be learning about computer networks, connecting computers to a network, understanding IP addresses, domain names, and origins of the Internet. Computers that are connected to each other form a network. Each computer on a network uses a network interface card to create the connection. A network interface card, or NIC, is a device, typically a circuit board card, used to connect a computer to a network. Most computers and mobile devices have a network card built into them. For older devices, a network card might need to be installed to connect to a network. Network cards are connected to servers using cables or wireless signals. A server is a general term for any computer that accepts requests from other computers that are connected to it and shares some or all of its resources, such as printers, files, or programs, with the connected computers. A file server runs software that coordinates the data flow among other computers in the network, which are called clients. The software that runs on the server is called a network operating system. Connecting computers in which one server computer shares its resources with multiple client computers is called a client-server network. Client-server networks are commonly used to connect devices in a local area network, or LAN, which is a network configuration that allows devices that are located in close proximity to each other, such as in a home or a small business, to be connected. In this figure, we're looking at a client-server LAN. On the far right, you'll see three PCs, PC1, PC2, and PC3, and note that PC3 is directly connected to a local printer. In this case, PC3 is the only computer that can print to that printer. This might represent, say, an accounting department where only the accountants have access to the check printing printer. You'll notice that PC1, PC2, and PC3 are all connected to the LAN switch, as is the network printer, the file server, the domain controller, and the router, which is the device that forwards the traffic from the inside network to the outside network, in this case, the Internet service provider, who provides access to the Internet. The key to the client-server LAN is the LAN switch. All devices connected to the LAN switch can communicate with each other and are said to be on the same network. Having computers connected in a client-server network can provide cost savings. For example, by connecting each client computer to a network, all of the connected devices can share the network printer, the file server, and have their logins authenticated by the domain controller. Most personal computer operating systems, including current versions of Microsoft Windows and Apple's Mac OS, have built-in networking capabilities. Also, some computer operating systems that can serve as network operating systems, such as Linux, are available on the Internet and can be downloaded and used at no cost. Not all LANs use the same kind of cables to connect to their computers. The oldest cable type is called twisted pair cable, which telephone companies have used for years to wire residences and businesses. Twisted pair cable has two or more insulated copper wires that are twisted around each other and are enclosed in another layer of plastic insulation. A wire that carries an electrical current generates an electromagnetic field around itself. The electromagnetic field can induce a small flow of electricity in nearby objects, including other wires. This induced flow of unwanted electricity is called electromagnetic interference, or EMI. In twisted pair wiring, the wires are twisted because wrapping the two wires around each other reduces the amount of electrical interference that each wire in the pair might pick up from other nearby current-carrying wires. The type of twisted pair cable that telephone companies have used for years to transmit voice signals is called Category 1 cable. Category 1 cable transmits information more slowly than other cable types, but it is also much less expensive. Cat 5e supports gigabit speed networks, and it's the minimum requirement for all modern-day networks. And Cat 6a supports 10 gigabit speeds, and is the recommended cabling for all modern-day networks. Many businesses and schools have Category 5 cable installed, but they're replacing it with Category 5E, 6, and 7 cabling as they upgrade their network hardware to handle the highest LAN speeds available today. You might hear these cable types called Cat 5, Cat 6, or Cat 7 by network technicians. Coaxial cable is insulated copper wire encased in a metal shield that is enclosed in plastic insulation. The signal-carrying wire is completely surrounded by the metal shield, so it resists electrical interference much better than twisted pair cable. Coaxial cable also carries signals about 20 times faster than Category 1 twisted pair. However, it is considerably more expensive. Because coaxial cable is thicker and less flexible than twisted pair, it is harder for installation workers to handle and thus is more expensive to install. You probably have seen coaxial cable because it is used for most cable television connections. You might hear this type of cable called coax by network technicians. Fiber optic cable systems transmit information using lasers to pulse beams of light through very thin strands of glass. In single-mode fiber, there's a single beam of light that is used. In multi-mode fiber, multiple beams of light are used and thereby produce higher speeds for transmitting data across the network. Fiber optic cable transmits signals much faster than either coaxial cable or any category of twisted pair cable. Because it does not use electricity, fiber optic cable is completely immune to electrical interference. It is lighter and more durable than coaxial cable, but it's harder to work with and more expensive than either coaxial cable or Category 5 or higher twisted pair cable. The price of fiber optic cable and the laser sending and receiving equipment needed at each end of the cable has dropped dramatically over time. Thus, companies are using fiber optic cable in more networks as the cost becomes more affordable. However, its main use today remains connecting networks to each other rather than being part of the networks themselves. Perhaps the most liberating way to connect computers in a LAN is to avoid using cables completely. Wireless networks use wireless transmitters and receivers that plug into or replace network cards to connect devices to a network without using cables. Wireless LANs are used to provide network services in many types of buildings and on school campuses, in retail outlets, and in homes and businesses. The figure you're looking at is the physical layout of a small wireless network that might be useful in a small office or a home. Connected to the wireless network are 2 desktop computers, 2 laptop computers, a shared printer, and 2 mobile devices. The only cable used in this configuration is the one that connects the wireless router to the internet connection. On the left of the figure, you can see there are specifications for various wireless network standards. 802.11a, 802.11b, 802.11g, 802.11n, and 802.11ac. They're ordered by speed, from slowest to fastest, and by order of release, from oldest to newest. All of these connection types, twisted pair, Cat 1, Cat 5, Cat 5e, Cat 6, and 7, coaxial, fiber optic, and wireless, are options for creating LANs. These LANs can, in turn, be connected to the internet or larger networks. Each computer on the network has a unique identification number called an IP, or Internet Protocol address. IP addressing uses a unique number such as 192.168.1.25 to identify each computer on the web. Most people, however, do not use an IP address to locate a website. Instead, they use its domain name. Until 2011, the IP addressing system used on the Internet was called IP version 4. IPv4 uses a 32-bit number to label each address on the Internet. The 32-bit address is usually written in 4 8-bit parts. In most computer applications, an 8-bit number is called a byte. However, in networking applications, an 8-bit number is often called an octet. Each octet has a decimal range of 0 to 255. Each part of a 32-bit IP address is separated from the previous part by a period, which is why the IP address format is referred to as the dotted decimal notation. You might hear a person pronounce this address as 192.168.1.25. The combination of these four parts provides nearly 4.3 billion possible addresses. Just multiply 256 times 256 times 256 times 256, and you get 4,294,967,296 possible addresses. Because each of the four parts of the dotted decimal number can range from 0 to 255, IP addresses range from 0.0.0.0, which would be written in binary as 32 zeros, to 255.255.255.255, which would be written in binary as 32 ones. In order to better understand IP addressing, view the IP address and subnet mask lecture for more detail. In the mid-1990s, the accelerating growth of the Internet created a concern that the world would run out of IP addresses within a few years. Originally, the nearly 4.3 billion addresses provided by IPv4 seemed sufficient for experimental research networks. However, by 2011, the supply of IP addresses was gone. The Internet Engineering Task Force, IETF, worked on several new protocols that could solve the limited addressing capacity of IP version 4, and in 1997 approved IP version 6 as the protocol that would replace IP version 4. The new IP version was implemented gradually over 20 years because the two protocols are not directly compatible. However, network engineers have devised ways to run both protocols together on interconnected networks. The major advantage of IP6 is that the number of addresses is billions and billions and billions times larger than the nearly 4.3 billion addresses available in IP version 4. As you can see, the math for IP version 6 is 3.4 times 10 to the 38th power would be the number of possible addresses that can be used in IP version 6. A domain name is a unique name associated with a specific IP address by a program that runs on an Internet host computer. This program, which coordinates the IP addresses and domain names for all computers attached to it, is called DNS, or the Domain Name System software, and the host computer that runs this software is called a domain name server. For example, the domain name CSIS.msjc.edu is a computer connected to the Internet for MSJC's Computer Information Systems (CIS) department, which is an educational institution.edu, and no other computer on the Internet has this same domain name. Domain names have a hierarchical structure that you can follow from top to bottom as you read the domain names from right to left. The last part of the domain name is called its top-level domain, or TLD. For example, DNS software on the Internet host computer that's responsible for the .com domain keeps track of the IP addresses for all of the institutions in its domain, including Amazon.com. Similarly, the DNS software running on the DNS server at Amazon.com keeps track of the company's other computers in its domain. Since 1998, the Internet Corporation for Assigned Names and Numbers, ICANN, has been responsible for managing domain names. In the 1980s, 6 top-level domains, TLDs, were created: .com, .edu, .gov, .mil, .net, and .org. Domains registered using the .com, .net, and .org TLDs have no restrictions. However, domain names that use the .edu, .gov, and .mil TLDs are restricted to certain types of organizations and for limited purposes. In addition to these original TLDs, ICANN created and manages additional TLDs called General TLDs or GTLDs. To expand the number of TLDs, some of the GTLDs include ones for specific countries, such as .us, which is approved for general use by any person or organization within the United States. However, the .us domain is most frequently used by state and local government organizations in the United States and by U.S. primary and secondary schools because the .edu domain is reserved for post-secondary educational institutions. Internet host computers outside the United States often use two-letter country domains instead of, or in addition to, the 6 general TLDs. For example, the domain name uq.edu.au is for the University of Queensland, UQ, which is an educational institution, .edu, in Australia.au. In May of 2016, ICANN announced a milestone as the number of GTLDs surpassed 1,000. Origins of the Internet. In the early 1960s, the U.S. Department of Defense undertook a major research project. Because this was a military project and was authorized as part of national security, the true motivations are not known with certainty, but most people close to the project believe it arose from the government's concerns about the possible effects of having a nuclear attack on military computing facilities. The Department of Defense realized that the weapons of the future would require powerful computers for coordination and control. The powerful computers of that time were all large mainframe computers, so the Department of Defense began examining ways to connect these computers to each other and to weapons installations that were distributed all over the world. The agency charged with the task was the Advanced Research Projects Agency, ARPA. During its lifetime, the agency has used 2 acronyms, ARPA and DARPA. DARPA is the current acronym used by the agency, which stands for Defense Advanced Research Projects Agency. DARPA hired many of the best communication technology researchers and for many years funded research at leading universities and institutes to explore the task of creating a worldwide network of computers. DARPA researchers soon became concerned about computer networks' vulnerability to attack, because networks at that time relied on a single central control function. If the network's central control point was damaged or attacked, the network would be unusable. Consequently, they worked hard to devise ways to eliminate the need for network communications to rely on a central control function. One of the first networking-related topics to be researched by the DARPA scientists was connectivity, or methods of sending messages over networks. The first computer networks were created in the 1950s. The models for those early networks were the telephone companies because most of the early wide area networks, WANs, used leased telephone company lines to connect computers to each other. In telephone company systems at the time, a telephone call established a single connection between sender and receiver. Once the connection was established, all data then traveled along that single path. The telephone company's central switching system selected specific telephone lines or circuits that would be connected to create the single path. This centrally controlled single connection method is called circuit switching. Although circuit switching is efficient and economical, it relies on a central point of control and a series of connections that form a single path. This makes circuit switch communications vulnerable to destruction of a central control point or any link in the series of connections that make up the single path that carries the signal. Packet switching is an alternative means for sending messages. In a packet switching network, files and messages are broken down into packets that are labeled electronically with codes for their origin and destination. The packets travel from computer to computer along the network until they reach their destination. The destination computer collects all the packets and reassembles the original data from the pieces in each packet. Each computer or router that an individual packet encounters on its trip through the network determines the best way to move the packet forward to its destination. Computers and other devices that perform this function on networks are called routers, and the programs they use to determine the best path for packets is called a routing algorithm. Thus, packet switch networks are inherently more reliable than circuit switch networks because they rely on multiple routers instead of a central point of control, and because each router can send individual packets along different paths if parts of the network are not operating. By 1967, DARPA researchers had published their plan for packet switching networks, and in 1969 they connected the first computer switches at 4 locations: the University of California at Los Angeles, the Stanford Research Institute, the University of California at Santa Barbara, and the University of Utah. This experimental WAN was called the ARPANET. The ARPANET grew over the next 3 years to include more than 20 computers. The ARPANET used the Network Control Protocol, or NCP, to enable each of those computers to communicate with other computers on the network. As more researchers connected their computers and computer networks to the ARPANET, interest in the network grew in the academic community. One reason for its increased interest in the project was its adherence to an open architecture philosophy. That is, each network could continue using its own protocols and data transmission methods internally. The open architecture philosophy includes 4 key points. 1. Independent networks should not require any internal changes to be connected to the Internet. 2. Packets that do not arrive at their destinations must be retransmitted from their source network. 3. Router computers do not retain information about the packets they handle. And 4. No global control will exist over the network. This open architecture philosophy was revolutionary at the time. Most companies that built computer networking products at the time, including IBM and Digital Equipment Corporation, put considerable effort into making their networks incompatible with other networks. These manufacturers believed that they could lock out competitors by not making their products easy to connect with products made by other companies. The shift to an open architecture approach is what made the Internet of today possible. In the early 1970s, Vincent Cerf and Robert Kahn developed a set of protocols that implemented the open architecture philosophy better than the Network Control Protocol, or NCP. These new protocols were called the Transmission Control Protocol and the Internet Protocol, which usually are referred to by their combined acronym TCP/IP. TCP includes rules that computers on the network use to establish and break connections. IP includes rules for routing of individual data packets. TCP/IP continues to be used today in LANs and on the Internet. The term Internet was first used in an article about TCP written by Cerf and Kahn in 1974. The importance of TCP/IP in the history of the Internet is so great that many people consider Vincent Cerf to be the father of the Internet. A number of TCP/IP-based networks independent of the ARPANET were created in the late 1970s and early 1980s. The National Science Foundation, NSF, funded the Computer Science Network, CSNet, for educational and research institutions that did not have access to the ARPANET. The City University of New York started a network of IBM mainframes at universities called the Because It's Time Network, or BitNet. Although the goals of the ARPANET were still to control weapons systems and transfer research files, other uses for this vast network began to appear in the early 1970s. In 1972, an ARPANET researcher named Ray Tomlinson wrote a program that could send and receive messages over the network. email had been born and rapidly became widely used in the computer research community. In 1976, the Queen of England sent an email message over the ARPANET. The ARPANET continued to develop faster, and more effective network technologies, like sending packets by satellite in 1976, increased the effectiveness of the ARPANET network. By 1981, the ARPANET had expanded to include more than 200 networks. The number of individuals in the military and education research communities who used the network continued to grow. Many of these new participants used the networking technology to transfer files and access computers remotely. The TCP/IP suite included two tools for performing these tasks. The File Transfer Protocol, or FTP, enabled users to transfer files between computers, and Telnet let users log into their computer accounts from remote sites. The first mailing lists also appeared on these networks. A mailing list is an email address that takes any message it receives and forwards it to any user who has subscribed to the list. Although file transfer and remote login were attractive features of these new TCP/IP networks, their improved email and other communications facilities attracted many users in the education and research communities. Mailing lists such as BitNet's listserv, information posting areas such as the Users News Network or Usenet newsgroups, and adventure games were among the new applications appearing on the ARPANET. Although the people using these networks were developing many creative applications, relatively few people had access to the networks. Most of these people were members of the research and academic communities. From 1979 to 1989, these new and interesting network applications were improved and tested with an increasing number of users. TCP/IP became more widely used as the academic and research institutions realized the benefits of having a common communications network. The explosion of PC users during that time also helped more people become comfortable with computing. The early 1980s saw continued growth in the ARPANET and other networks. The Joint Academic Network, JANET, was established in the United Kingdom to link universities there. Traffic increased on all of these networks, and in 1984, the Department of Defense split the ARPANET into two specialized networks. The ARPANET would continue its advanced research activities, and the MILNET, military network, would be reserved for military uses that required greater security. By 1987, congestion on the ARPANET caused by a rapidly increasing number of users on the limited-capacity leased telephone lines was becoming severe. To reduce the traffic load on the ARPANET, a network run by the NSF called NSF-Net merged with another NSF network called CS-Net and with BitNet to form one network that could carry much of the network traffic that had been carried by the ARPANET. The resulting NSF-Net awarded a contract to Merit Network Incorporated, IBM, Sprint, and the state of Michigan to upgrade and operate the main NSF-Net backbone. A network backbone includes the long-distance lines and supporting technology that transport large amounts of data between major network nodes. By the late 1980s, many other TCP/IP networks had merged or established interconnections. The image on this slide summarizes how the individual networks described in this section combined to become the Internet as it is known today. As PCs became more powerful, affordable, and readily available during the 1980s, companies increasingly used them to construct LANs. Although these LANs included email software that employees could use to send messages to each other, businesses wanted their employees to be able to communicate with people outside their corporate LANs. The National Science Foundation, NSF, prohibited commercial network traffic on the networks it funded. So businesses turned to commercial email services. Larger firms built their own TCP/IP-based WANs, wide area networks, that used leased telephone lines to connect field offices to corporate headquarters. Today, people use the term intranet to describe LANs or WANs that use TCP/IP but do not connect to sites outside of a single organization. Although most companies allow only their employees to use the company intranet, some companies give specific outsiders, such as customers, vendors, or business partners, access to their intranets. These outside parties agree to respect the confidentiality of the information on the network. An intranet that allows selected outside parties to connect is often called an extranet. In 1989, the NSF permitted two commercial email services, MCI Mail and CompuServe, to establish limited connections to the Internet that allowed their commercial subscribers to exchange email messages with the members of the academic and research communities who were connected to the Internet. These connections allowed commercial enterprises to send email directly to Internet addresses and allowed members of the research and education communities on the Internet to send email directly to MCI Mail and CompuServe addresses. The NSF justified this limited commercial use of the Internet as a service that would primarily benefit the Internet's non-commercial users. People from all walks of life, not just scientists and academic researchers, started thinking of these networks as a global resource that we now know as the Internet. Information system professionals began to form volunteer groups, such as the Internet Engineering Task Force, IETF, which first met in 1986. The IETF is a self-organized group that makes technical contributions to the engineering of the Internet and its technologies. The IETF is the main body that develops new Internet standards. Although the network of networks that is now known as the Internet had grown from 4 computers on the ARPANET in 1969 to more than 300,000 computers on many interconnected networks by 1990, the greatest growth in the Internet was yet to come. In Session A.2, you'll be learning about the growth of the Internet, the evolution of the web, origins of hypertext, evolution of the web browser, businesses that provide Internet access, bandwidth, and types of connectivity. A formal definition of the term Internet, which was adopted in 1995 by the Federal Networking Council, FNC, is shown here. The researchers, who had been so involved in the creation and the growth of the Internet, accepted it as part of their working environment. But people outside the research community were largely unaware of the potential offered by a large interconnected set of computer networks until the 1990s. Realizing that the Internet was becoming much more than a scientific research project, the U.S. Department of Defense finally closed the research portion of its network, the ARPANET, in 1995. The NSF also wanted to turn over the Internet to others so it could return its attention and funds to other research projects. The process of shutting down the ARPANET and privatizing the Internet began in 1991 when the NSF eased its restrictions on Internet commercial activity. Businesses and individuals continued to connect to the Internet in ever-increasing numbers. The opening of the Internet to business enterprise helped increase its growth dramatically. However, another development worked hand in hand with the commercialization of the Internet to spur its growth. That development was the technological advance known as the World Wide Web. Some experts estimate that the Internet experiences upwards of 3 billion unique users each day. This number is certain to continue to rise as more and more people use convenient mobile devices to access the web. 2 important innovations played key roles in making the Internet easier to use and more accessible to people who were not research scientists. The first innovation, hypertext, connected the content stored on the networks and made the content more accessible. The second innovation was the web browser itself, which provided users with a tool that made it possible to find and access that content. In 1945, Vannevar Bush, who was the director of the U.S. Office of Scientific Research and Development, wrote an Atlantic Monthly article about ways that scientists could apply to peacetime activities the skills they learned during World War II. The article included a number of visionary ideas about the future uses of technology to organize and facilitate efficient access to information. Bush speculated that engineers eventually would build a machine that he called the MEMEX, a memory extension device that would store all of a person's books, records, letters, and research results on microfilm. Bush's MEMEX would include mechanical aids to help users consult their collected knowledge quickly and in a wide variety of ways. In the 1960s, Ted Nelson described a similar system in which text on one page links to text on other pages. Nelson called his page linking system hypertext. Douglas Engelbart, who also invented the computer mouse, created the first experimental hypertext system on one of the large computers of the 1960s. In 1976, Nelson published a book, Dream Machines, in which he outlined Project Xanadu, a global system for online hypertext publishing and commerce. In 1989, Tim Berners-Lee and Robert Calio were working at CERN, the European Laboratory for Particle Physics. Berners-Lee and Calio were trying to improve the laboratory's research document handling procedures. CERN had been using the Internet for 2 years to circulate its scientific papers and data among the high-energy physics research community throughout the world. However, the Internet did not help the agency display the complex graphics that were important parts of its theoretical models. Independently, Berners-Lee and Calio each proposed a hypertext development project to improve CERN's document handling capabilities. Over the next 2 years, Berners-Lee developed the code for a hypertext server program and made it available on the Internet. A hypertext server is a computer that stores files written in the hypertext markup language and lets other computers connect to it and read the files. Berners-Lee, who was familiar with the standard generalized markup language, SGML, a set of rules that organizations have used for many years to manage large documents, filing systems, began developing a subset of SGML that he called the Hypertext Markup Language, HTML. HTML, like all markup languages, includes a set of codes or tags attached to text. These codes describe the relationship among text elements. For example, HTML includes tags that indicate which text is part of a header element, which text is part of a paragraph element, and which text is part of a numbered list element. One important type of tag is the hypertext link tag. A hypertext link, or hyperlink, points to another location in the same or another HTML document. HTML documents can also include links to other types of files, such as word processing documents, spreadsheets, graphics, audio clips, and video clips. An HTML document differs from a word processing document because it does not specify how a particular text element will appear. For example, you might use word processing software to create a document heading by setting the heading text font to Arial and its font size to 14 points and its position to centered. The document displays and prints these exact settings whenever you open the document in the word processor. In contrast, an HTML document surrounds the text with a pair of heading tags to indicate that the text should be considered a heading. Many programs can read HTML documents. The programs recognize the heading tags and display the text in whatever manner they normally display headings. Different programs might display the heading text differently. Like the Internet itself, standards for HTML are not controlled by any central managing organization. Standards for technologies that are used on the web, including HTML, are developed and promulgated by the World Wide Web Consortium, W3C, an international organization formed in 1994 and sponsored by universities and businesses from around the world. Berners-Lee was appointed director of the W3C when it was formed and continues in that position today. A web browser displays an HTML document in an easy-to-read format in its graphical user interface. A graphical user interface, GUI, pronounced GUI, is a way of presenting program output using pictures, icons, and other graphical elements instead of just displaying text. All personal computers now use a GUI. The GUI presented in web browsers played an important part in the rapid growth of the web. The first web browsers were text-based. and lacked the graphical elements such as buttons that make today's browsers so easy to use. The figure on your screen shows a web page displayed in links, a text-based browser that was commonly used in the early days of the web. As you can see, it does not look very much like the web pages displayed by web browsers today. As the NSF-Net converted the main traffic-carrying backbone portion of its network to private firms, it organized the network around 4 network access points, NAPs, pronounced NAPs. These were operated by 4 different telecommunication companies, and these 4 companies and their successors sell access to the Internet through their NAPs to organizations and businesses that, in turn, provide Internet access to other businesses and individuals. These firms are called Internet Access Providers, IAPs, or Internet Service Providers, ISPs. Most of these firms call themselves ISPs because they offer more than access to the Internet. ISPs usually provide their customers with software to connect to the ISP, browse the web, send and receive email messages, and perform functions such as file transfer and remote logon to other computers. ISPs often provide network consulting and web design services to their customers. Some ISPs have developed a range of services that include network management, training, and marketing advice. Large ISPs that sell Internet access and other services to businesses are called Commerce Service Providers, CSPs, because they help businesses conduct business activities, or commerce, on the Internet. The larger ISPs sell Internet access to smaller ISPs, which then sell, access, and service their own business and individual customers. The hierarchy of the Internet service providers appears in the figure on your screen. One of the most important differences among different levels of ISPs is the connection bandwidth an ISP can offer. Bandwidth is the amount of data that can travel through a communication circuit in 1 second. The bandwidth an ISP can deliver depends on the connection it has to the Internet and the connection you have to the ISP. The available bandwidth for any type of network connection between 2 points is limited to the narrowest bandwidth that exists in any part of the network. For example, if you connect to an ISP through a regular telephone line, your bandwidth is limited to the bandwidth of the telephone line, regardless of the bandwidth connection that the ISP has to the Internet. Bandwidth for Internet connections is measured the same way as bandwidth for connections within networks, in multiples of bits per second, BPS. Common terms are kilobits per second, kbps, which is 1024 bits per second, megabits per second, or mbps, which is 1,048,576 bits per second, and gigabits per second, gbps, which is 1,073,741,824 bits per second. Sometimes computer users are confused by the use of bits to measure bandwidth because file sizes are measured in bytes. As explained earlier, a byte is 8 bits. It's abbreviated with an uppercase B. Most LANs today run either fast Ethernet, which operates at 100 megabits per second, or gigabit Ethernet, which operates at 1 gigabit per second. Some older LANs use an earlier version of Ethernet that operates at 10 megabits per second. The effective bandwidth of wireless LANs depends on the distance between computers and what types of barriers the wireless signals must pass through. For example, wireless signals travel more easily through glass than steel. Most wireless LANs achieve an operating bandwidth of between 2 megabits per second and 10 megabits per second, although newer wireless devices with more than 100 megabits per second are available. When you extend your network beyond a local area, either through a WAN or by connecting to the Internet, the speed of the connection depends on the type of connection. One way to connect computers over networks over longer distances is to use regular telephone dial-up service. Regular telephone service to most U.S. residential and business customers provides a maximum bandwidth of between 28.8 kilobits per second and 56 kilobits per second. Once you connect your computer, which communicates using digital signals, to another computer through the telephone line, which uses analog signals, you must convert the signals from one form to the other. The device that performs the signal conversion is a modem, which is short for modulation-demodulation. Converting a digital signal to an analog signal is called modulation. Converting that analog signal back to a digital signal is called demodulation. A modem performs both functions. It acts as a modulator and a demodulator. Some telephone companies offer a higher grade of service that uses one of a series of protocols called Digital Subscriber Line, or DSL, or Digital Subscriber Loop, also DSL. The first technology that was developed using a DSL protocol is called Integrated Services Digital Network, or ISDN. ISDN service has been available in various parts of the United States since 1984. Although considerably more expensive than regular telephone service, ISDN offers bandwidth of up to 256 kilobits per second. ISDN is much more widely available in Australia, France, Germany, Japan, and Singapore than in the United States because the regulatory structure of the telecommunications industries in those countries encouraged rapid deployment of this new technology. All technologies based on the DSL protocol require the implementing telephone company to install new equipment at its switching stations, which can be very expensive. New technologies that use the DSL protocol are currently being implemented around the world. One of those, the Asymmetric Digital Subscriber Line, or ADSL, offers transmission speeds ranging from 16 to 640 kilobits per second from the user to the telephone company, and from 1.5 to 9 megabits per second from the telephone company to the user. Asymmetrical, representing that you have one speed going out and a different speed on your download. Businesses and large organizations often obtain their internet connection by connecting to an ISP using higher bandwidth telephone company connections called T1s, 1.544 megabits per second, and T3s, 44.736 megabits per second. T1s and T3s were originally acronyms for Telephone 1 and Telephone 3, respectively, but few people use these terms any longer. Companies with operations in multiple locations sometimes lease T1s and T3 lines from telephone companies to create their own WANs to connect their locations to each other. T1 and T3 connections are much more expensive than plain old telephone service, POTS, or Integrated Services Digital Network, ISDN, connections. However, organizations that must link hundreds of thousands of individual users to WANs or to the Internet require the greater bandwidth of a T1 or a T3 connection. Smaller firms can save money by renting access to a partial T1 connection from a telephone company. In a partial T1 rental, the connection is shared with other companies. The network access points operate the Internet backbone using a variety of connections. In addition to T1 and T3 lines, the NAPs use newer connections with bandwidths of more than 1 gigabit per second, in some cases exceeding 10 gigabits per second. These connection options use fiber optic cables and are referred to as OC3, OC12, and so forth. OC is short for optical carrier. NAPs also use high bandwidth satellite and radio communication links to transfer data over long distances. A group of research universities and the NSF now operate a network called Internet 2 that has backbone bandwidths greater than 100 gigabits per second. The Internet 2 project continues the tradition of the DARPA scientists by sponsoring research at the frontiers of network technologies. Another connection option is to connect to the Internet through a cable television company. The cable company transmits data in the same cables used to provide television service. Cable speeds far exceed those of existing dial-up and ISDN connections. Yet another option that is commonly used in remote geographic areas where cable connections are more difficult to install is by satellite, which uses satellites orbiting the Earth to send and receive signals from dishes mounted on rooftops. Today, most satellite ISPs install transmitters on the dish antenna. This allows two-way satellite connections to the internet. Because satellite connections are affordable and easy to install, they are now used throughout the world and not just in remote geographic areas. The actual bandwidth provided by all of these internet connection methods varies from provider to provider and the amount of traffic on the internet. During peak operating hours, traffic on the internet can become congested, resulting in slower data transmission. The bandwidth achieved is limited to the lowest amount of bandwidth available at any point in the network. That's it for this lecture. Until next time, may your internet connection always be at its best. If you liked this video, please click the like button and leave us a comment down below. I also would appreciate it if you would subscribe to our YouTube channel. Also, click the notification bell so that you'll be notified when new videos are posted.